Yes, welcome everyone. I'm very happy to introduce Francesco Leofante today. He's a research fellow at Imperial College in London, and his research focuses a lot on safe and explainable AI, especially counterfactual explanations, what he will present us today. And I found out today that he wrote recently a book which will be published soon in May, which is about robustness in explainable AI. So very curious, waiting for this book, and happy to have you here today. So please, Francesco.
Thank you. Thank you very much. Hi, everyone. I will keep the introduction short, but I do counterfactual explanations. I mostly work on explainability, right? I've done quite a few things in AI, but most recently, meaning over the last couple of years, I've been mostly focusing on counterfactual explanations for machine learning models, and I've studied sort of as the title of this talk suggests, I've studied their robustness. Okay, so I will clarify what this means during the talk. Just a disclaimer: I'm not a robust optimization person, but I did use robust optimization in some papers to provide answers, to this robustness issue, the robustness problem in counterfactuals. But mostly, the techniques I use, they're based on optimization, discrete optimization techniques mostly. So hopefully you will all find something interesting in here. Okay. So now let's start with the talk, the actual one. So robustness issues and counterfactual explanations. Now, counterfactual explanations, I don't know if you're aware, but they're a very popular type of explanations that can be used to provide recourse recommendations to users. Okay, users that have been negatively affected by the decisions of machine learning models. What do I mean by recourse? And let me give you a bit of an example. So this is kind of a standard example that you would find in the literature on counterfactuals. We have a person that applies for a loan. Here we are assuming that the loan application can be characterized in terms of three features: age of the applicant, loan amount, and loan duration. Okay. And now we assume that there is a machine learning model, an AI model somewhere that is used to predict whether the person will be able to repay their loan in time. Okay. And based on this prediction, the financial institution, for instance, might decide whether to grant the loan or not. Now, for this person here, the loan was denied. So how can we help them, right? They still need a loan. How can we help them get the loan, right? So this is the problem of recourse, algorithmic recourse in particular. We have this person, the machine learning model, the AI model produced a decision that is not quite positive for them. How do we help them change the situation? We can do this using counterfactual explanations. And in particular, wait a second, why is it not moving? There you go. Counterfactual explanations that look like this. Basically, in a nutshell, a counterfactual explanation is typically defined as a set of minimal changes that need to be applied to the input of a machine learning model for the model to produce a different outcome, typically a positive one. Okay. So in this case, for instance, we see that a possible counterfactual could read like this. So your loan application was rejected. However, the loan would have been accepted, would have been granted had you asked for a bit less money. Okay, so this is what a counterfactual can do, and this is how we can use the counterfactual to basically provide these recourse recommendations that we want to generate. Okay. Now, how do we compute counterfactuals? I will focus here on the case of machine learning models, right? So the AI model under analysis is a machine learning model. And in particular, we start from this instance X, that is the point we would like to explain. So this is the rejected loan application for which we want to compute recourse. We assume in this case, for the sake of this talk, we assume to be working with binary classifiers. That doesn't have to be the case in general, but just for simplicity, we have a classifier M, say a neural network, that produces an undesirable outcome for X. Okay, so in this case, for instance, we assume that M of X equals 0 means loan rejected. Okay. And now, of course, we want to have it accepted. The last ingredient is this distance function. So we assume the availability of a distance function over the input space from which X is drawn, and that will also be the space from which the counterfactual is drawn. And now this counterfactual X prime is nothing but the solution of this optimization problem here, where we're trying to find an X prime that sort of minimizes this loss that you can see on the slide. And now in this formulation, we have kind of two terms. The first one is L, which is typically a differentiable loss function that kind of steers the search for an X prime, for a counterfactual X prime, for which the model M produces the desired classification, 1 in our case. Okay, so this is the property that in the literature on counterfactual is typically referred to as validity. So we want a point that effectively flips the classification. The other term in the loss function, in the objective function, is this lambda times D. D is the distance function, right? And lambda is just a tunable sort of a hyperparameter that we can use to tune the relative importance between the two terms, okay? So what is the intuition behind this formulation? The idea is that we want to find a point, X prime, that is minimally different from X, right? Such that, however, X prime needs to satisfy an additional constraint that is M of X prime, so the classification that the model produces for this point needs to be positive, okay? Why minimizing distance? Because typically, especially in the context of algorithmic recourse, distance is typically used as a proxy for the effort that a person will have to put into achieving the changes that are prescribed by the counterfactual, okay? So this is kind of, counterfactuals 101, a few minutes on how to compute counterfactuals and, what they can be used for. Now, getting a bit more into the topic of this talk, let's focus on this idea of minimizing distance, okay? So minimizing distance typically results in, or at least the idea is that you would like to compute counterfactuals as instances that lie exactly at the decision boundary of your machine learning models, okay? Now, if you look at this slide here, what I'm reporting on this slide is a screenshot from a paper that you see referenced at the bottom. Now, what we are looking at here is the input space of a classifier partitioned into two regions by the classifier, right? So we have blue region, which is, say, reject region, if we think about the loan, red region, which is the region of inputs that are accepted, for which the loan is accepted. And then we have the dashed line, which is the decision boundary of the machine learning classifier, okay? Now, it turns out that, and this is something that was demonstrated in the paper, it turns out that algorithms to compute counterfactual explanations, at least those algorithms that are solving the optimization problem that we've seen in the previous slide without any additional sort of refinement or constraint, these algorithms tend to return counterfactual explanations that are indistinguishable from adversarial examples. Now, if you're familiar with the term adversarial examples, if you know what they are, these are effectively kind of blind spots of your classifier, right? So adversarial examples are points for which the classifier doesn't know what to say. Sort of, I'm simplifying it a lot. But the idea is that an adversarial example is a point for which your model misbehaves, okay? Now, based on this high level and simplified definition of what an adversarial example is, I hope you can appreciate that using an adversarial example to explain the behavior of a model, and especially if you think about using these these inputs to generate recourse recommendations for users, this is probably not a good idea, right? So the point is that maybe when computing explanations, you want to use or you want to base your recourse recommendations on something that is a bit more reliable. What do I mean by reliable? I mean robust, right? Because the problem here is that when you compute a counterfactual explanation that lies exactly in the decision boundary, any sort of small perturbation that might be applied to the counterfactual or to the model or to the input itself, right, might result in might invalidate counterfactual explanations, okay? So, and this is this is kind of the core problem that I've worked on over the last couple of years. We have this survey here, you see at the bottom of the slide, a survey that we published last year, where we talk a lot about, the robustness problem, the different notions of robustness, because of course, sort of depending on where you apply the perturbation, you end up obtaining different variations, let's say, of this robustness problem. Now, for this talk, I will only focus today. I will only focus on three notions, which are listed here. So, robustness to input changes, and model multiplicity. But there's more, right? There is, as I was, I don't know if you joined the meeting at the beginning, I was talking about noisy execution. Yanis has a paper on that. You will also find this sort of a description of this notion in the survey paper. But let's start with some concrete examples, okay? Robustness to input changes. What do I mean when I say that counterfactual explanations may lack robustness to input changes? Consider this cartoon here. Now, what we see here is, again, the input space of a classifier. Now, obviously, the decision boundary here is, I drew a perfect circle, quite unlikely in practice, but I did it just to, convey the main idea. We see here, the classifier partitions the input space into two regions, red region inside the circle, that would be, say, for instance, rejected loans, and then we have green region outside. Now, we start from our application, our applicant, right? That's kind of that we've been using as a running example. So far, so good. We see that this instance is rejected. The loan application for this instance is rejected. So what do we do now? We might want to generate a counterfactual explanation for this point that would be the closest input to the original one for which the loan is accepted. And for instance, this could be this black dot here, right? Now, the numbers are not necessarily meaningful, but again, I hope this is kind of helping you get an idea of what it means to generate a counterfactual. Now, suppose a new application comes in, okay? This application is actually very similar to the original one. We can see both on the left-hand side, the two inputs are closed in input space, but also if we look at the right-hand side, we see that the applications are basically the same. There's only a £1,000 difference in the loan amount, okay? Now, this application is processed in the same way as the original one, so the loan is still rejected. However, when we compute a counterfactual explanation for this point by minimizing distance, we end up obtaining this white dot, which is actually pretty far away and pretty different from the original counterfactual, or rather for the counterfactual that we computed for the original application, okay? Now, you might wonder, so what? Who cares? Well, this is, we claim, it's a bit of a problem. We're having a bit of a problem here because we have two inputs that are very similar. They're very close to each other, right? But these two inputs, these two individuals receive very different recourse recommendations, okay? And this is a bit, it can be troublesome because when you think about the way in which counterfactuals are used, or at least, advocated, their use is advocated in AI, I can think about a number of challenges here, and I'm only mentioning a few here. So trust. The first one is, imagine the two users know each other, right? And they discuss their situations, and they compare the recourse recommendations they received, and now all of a sudden they observe this kind of sort of lack of stability, lack of robustness, as we call it, which results in very different recommendations. Now, are we sure the explanation algorithm was actually explaining the model, right? Because, judging by how different the recourse recommendations are, we might be confused, right? We might wonder, like, is this really explaining anything at all? We also have a fairness issue, right? Because we have two inputs, as I said, two inputs that are very similar and they get very different recommendations. Why is that happening? And now imagine if the difference is not in terms of loan amount, but what if the difference entails a difference in protected features, for instance, right? This is obviously something you don't want to have. And reliability, whenever your explainer lacks robustness, uncertainty in the way data is collected, but also the way in which data is used to train the model might actually impact the robustness or the reliability of your explanation. Even worse, There is this paper here. It's a like in machine learning terms, it's a fairly old paper. So NeurIPS 2021, where authors have shown that models, neural networks in particular, can actually be trained to exhibit this behavior. So models can be trained in an adversarial way to produce counterfactual explanations that are different for sort of inputs that differ, as you can see in these plots, they can differ by a delta. So what you see in the plot is kind of the loss landscapes. On the left-hand side, we see the loss landscape of a model that has been trained with, vanilla training. And you see we have these two inputs, x and x plus delta. So these are the two similar inputs. And in a normal setting, sort of in a non-adversarial setting, we see that the algorithm A, which is used to compute recourse recommendations for these two inputs, kind of, it converges for the two inputs. They kind of, both of them, the algorithm results in two counterfactual explanations that are very sort of similar, right? The two blue stars are close enough. But now if we move to figure B, where we see the loss landscape for the model that has been trained using adversarial training, anyway, the technique they proposed in that paper, we see that the two inputs get very different explanations. So this is a problem, right? Now, how do we solve it? In this paper here, linked at the bottom, we proposed together, this is a paper that we published last year at AAAI with Nico Potica, a colleague from the University of Cardiff. Basically, in this paper, what we tried to understand why algorithms to generate counterfactual explanations lack robustness, right? And the first sort of the answer to this question is kind of fairly straightforward when you think about it. If your explainer only returns single nearest counterfactual explanations, that is, you give me an input and you only compute one counterfactual that is the closest one, your explainer is bound to lack robustness, right? Because any small change in the input will necessarily result in another solution, right? And sort of the severity of this instability, let's say, or in other words, sort of how far your counterfactual can jump, let's put it this way, can also be influenced by factors such as the shape of the decision boundary. Look at this slide here. Again, the usual input space, right? Now you see the decision boundary, the way it looks here. You definitely see that decision boundary plays a role. So what is the solution? Well, the solution we proposed was to move away from the single nearest counterfactual paradigm, and instead of returning single explanations, we propose to return entire sets of explanations, right? So why sets? Because with a set, you can actually achieve a better characterization of the decision boundary, which in principle helps with robustness. Now, there is still a problem here. We cannot, our aim is to use explanations in practice. And if you return sets that are too large, you might end up overwhelming the user, right? So you don't want to return too many explanations to the user, because kind of returning too many explanations is possibly the same as not returning any explanation at all, right? So not very useful. So what we proposed to do was to use diversity as a way to, in a way, contain, reduce the size of these sets while also preserving robustness. If you're not familiar with this concept of diversity, well, as the name suggests, kind of a metric that measures how different your explanations are within a set, right? So why is diversity important in general? Because there's no point in returning a set of explanations that are all similar, because why are you returning a set if they're all the same, right? So you want to make sure that they're sort of nicely spread, along the decision boundary. And in the paper, what we kind of, and sort of the idea behind this or kind of the intuition behind this idea is that by returning sets in practice, you can be you can leverage these sets for to generate explanations in a way that is kind of depicted here. So you imagine you have your two inputs that are similar. Now each applicant receives a set of explanations, right? Some explanations will be different. As you can see, each applicant receives two explanations here, and there is only some partial overlap between these two sets, But this is what we think could help sort of, it definitely help mitigates the robustness issue in terms of when you think about robustness as a sort of as a machine-centric metric. We are kind of trying to do some additional some follow-up work to actually try and understand whether this kind of overlap is also useful from a cognitive kind of point of view, right? So our intuition and or hope is that having a partial overlap or some degree of overlap between sets would also sort of reduce sort of the sort of surprise, it reduce surprises that, that and hopefully will help users understand recommendations a bit better. How do we compute these counterfactuals? We basically, in the paper, we instantiated the whole framework using a very simple nearest neighbor counterfactual explainer. So the idea is that you start from an input that has been rejected. This is your orange dot. And then you do nearest, you identify what some people call nearest unlike neighbors. So these are instances that belong to the opposite class now, right? But these instances are still not too far from the input because we still care about minimizing distance, right? So basically what we do is we kind of go through the data set, identify inputs, I should mention the data set that has been used to train the machine learning classifier. We go through this data set, we identify training instances that belong to the opposite class. We filter out distances that are too far away because we care about distance. Now, if you look at, bottom left, diversity kicks in. We remove instances that are too similar to each other, kind of. As I said, we want to kind of tame this problem of having two big sets. We use diversity to filter out candidates. And then in the last step, if you really want to have your counterfactuals, that lie exactly at the decision boundary, you can do some line search, for instance, and optimize further. Otherwise, you can just stop and return the blue dots as counterfactual explanations. There's a trade-off here. If you really care about distance, which don't quote me on that, but I don't know if it's a good idea, but it depends on the application, of course. But if you really care about distance, then go ahead and minimize. But if you care about other properties, such as plausibility of your explanations, plausibility means that your counterfactual explanations are aligned with the manifold, right? So basically they are in distribution. Then if you care about this other property, then maybe do not minimize too much, okay? And this is something that we also observed in our experiments. I will not bother you with too many numbers here because I know that reading tables is always challenging in presentations, but I just wanted to show you that we did our homework. So what we did, we compared our approach with DICE, which is a very popular algorithm to generate sets of counterfactuals. Mind you, DICE doesn't optimize for robustness, okay? So what we wanted to observe, kind of the idea behind our experiments is the following. We wanted to test whether the way we constructed our sets could actually improve the robustness of our explanations. Now, in the paper, we defined a couple of notions of robustness. Again, I didn't want to bother you with those details. If you have questions, even after this talk, feel free to email me. But the idea is now we compare two different methods that generate sets of explanations, and we want to see what happens in terms of robustness. And in terms of robustness, what we observe is that on average, our construction reduces this kind of instability problem with some variability, of course, depending on the data set. And the other interesting kind of bonus point, which we were not necessarily optimizing for, is that we ended up achieving better diversity and lower runtime than DICE. Now, DICE solves a very sophisticated optimization problem. So I think that can actually explain the increased runtime. And potentially the variability that you observe in this table as well. You see that sometimes if you look at the second column, for instance, you see there's the variance is a bit it's quite high. So there is a lot of variability in the process, but our algorithm was fairly stable in that regard. So there was kind of a nice additional result for us. So this is kind of wrapping up input changes. I would like to move on to another notion of model change, another notion of robustness, or lack thereof. And now I would like to focus on model changes. Okay, so we're not talking about inputs anymore. Now we're talking about changes that can occur in the classifier. Okay, so I have a bit of a another example here to sort of walk you through this problem. So we start from a neural network that has been fully trained. Okay, so the network is good to go. We deploy. We deploy the network and we use it to, as always, decide whether the poor guy gets a loan or not. And in this example, we see that the applicant doesn't get the loan. So what do? We compute a counterfactual explanation for this person because we want to generate recourse recommendations. Nothing new until here. Now, imagine, as I said, the model has been deployed, which basically means that quite a few of such iterations might happen in practice. And what happens is that after a few steps at the end here, we might end up having effectively new data, right? Because this is kind of new data corresponding to all the new to all the applications that kind of came through from T0 to Tn. And now with this new data, we might actually want to use the new data to improve the performance of our model, right? Why not? We have new information available. Let's use it to make our AI model better. So we do it. We use it, we do some fine tuning, for instance, on this model based on these new inputs. And as a result of the fine tuning, some of the parameters of the neural network will change, right? So again, nothing sort of, mind blowing here. We do fine tuning, some parameters change. And you might wonder now, why is this a problem for counterfactuals? Well, the problem is here, actually. You remember that counterfactuals are typically computed as points that lie exactly at the decision boundary. You change the parameters of your network, you might end up changing the shape of the decision boundary, which basically means you might invalidate your previously valid counterfactual explanation, right? Now, why is this a problem? Well, this kind of shifts or, this kind of changes in the decision boundary, they might be due to shifts in the distribution of your inputs, right? And, these kind of shifts, they occur. Like if you ever played with machine learning or, read something about machine learning, you know that, this kind of distribution shifts happen naturally. And now this is a problem, right? Because kind of we have the situation where if a shift happens, right, this might impact the quality, in fact, the validity of your counterfactuals. And now we have a dilemma here. Imagine, the financial institution that is using the machine learning model here. They have two options. The first option is to say, you know what, my new inputs suggest I should reject your application, right? But I'm a very, I'm a very good bank, and I'll kind of, I'll keep my promise, right? So my old counterfactual recommended some changes, and I will keep my promise despite the new evidence that comes with this, or with the new data. The other option is kind of at the other end of the spectrum. We say, I'm so sorry. I know I suggested a different counterfactual before. But now I changed my mind. Okay. Now, of course, we know, luckily for us, we know that loan applications and decisions around loan applications are not that simple, but I hope you get the idea here. Okay. So again, a solution that we proposed with some colleagues here at Imperial, Jay Jiang is the PhD student that I'm co-supervising with Francesca Toni here at Imperial. And we proposed a nice approach that is kind of rooted in verification of machine learning models. I'll explain. Model changes, right? We don't have a way to quantify them beforehand, right? We don't have a way to foresee how a model will change as a result of fine-tuning. But what we can do is as I'm saying here in the slide, we can take a certification perspective and kind of make some assumptions on the shape and magnitude of these changes, right? And based on these assumptions, we can actually reason about this type of noise, if you will, and we can actually incorporate this noise into the counterfactual generation process to ultimately generate counterfactual explanations that are robust. Now, how do we do it? We do it using interval neural networks. Okay, so on the left-hand side, you'll see a standard feed-forward neural network, two inputs, two ReLU nodes, and two outputs, okay? An interval neural network is a neural network where the weights are intervals, as the name suggests, okay? What is interesting about this object? The interval neural network is mapping points to intervals, right? It's not points to points as you normally have when you do classification with a standard network, right? Input map to a class. Now, with an interval neural network, we map points to entire intervals, and we can use this to perform some sort of uncertainty quantification, if you will, okay? To do this, you need to redefine the classification semantic of your network. Oh, sorry, before we get there, I should mention one thing. How do we get these intervals, right? Because this is an important point. These intervals, you remember at the beginning of this slide, I said we need to make assumptions on the shape of these changes, right? And that's how we build the intervals. For instance, we start from this original network and we say, you know what, I think my changes will be, L infinity, sort of a 0.1 change under L infinity norm, right? And then you build your intervals that way. There is freedom on how you build these changes, right? You can do whatever you want. If you have more sort of, domain knowledge, go ahead. But the idea is that we need to make an assumption on the shape of these changes because that is what will be used to build the intervals. Now, once we have the interval neural network, as I was trying to say earlier, we need to redefine the classification semantics of this object. Because as I said, the interval neural network is mapping a point to an interval, okay? So how do we interpret the outputs of an INN? I've written three cases. We have this, this kind of representation of three cases. Case number one, assuming, as always, a binary classification setting, we'll have a case in which there is a perfect separation between the two intervals, and in particular, class C, the interval corresponding to class C, will always be above the interval for class 1 minus C, okay? So this is a case in which we can say with 100% certainty that the point is classified as C. And this could be, for instance, the red region in this picture, right? So all points rejected. Then we have the opposite, where the interval for 1 minus C is always above interval for C. And this could be the green region, right? So always classified as C, no matter the change, okay? And then we have somewhere in between. So when we have overlap between the intervals, this is a case where depending on how you change the weight, right? Depending on how you pick the weights from these intervals, you may or may not, you may land either in the green area or in the red area, okay? So the idea is that now we can use this object and the classification outcomes of this object to effectively derive algorithms that can kind of leverage this uncertainty quantification to generate points that lie in the green area, sort of 100%, with 100% certainty. And we proposed a couple of approaches to do so. Crucially, and maybe interestingly for some of you in the audience, one of them relies on robust optimization, right? Because we're kind of solving this optimization problem that you've seen at the beginning with some noise, and the noise is kind of the intervals on the weights of this network, okay?
Francesco, a short
Yes.
question. So actually, how do you get these output intervals? So, I mean, the neural network is not linear, doesn't have a nice structure in the weight, so you cannot just take the lower interval ends, right? So,
Yeah, so what we did, at least in fact, in all the papers, we made an assumption on the activation function. So we only consider piecewise linear activation functions, okay? No, fancy stuff. And then we compute the output reachable sets by solving optimization problems where basically you have a variable that is the lower bound, say for y0, okay? Y0 is one of the outputs. And then you'll define the lower bound of the interval for y0 as your variable that you kind of try to minimize, okay? And then you compute. This is, by the way, based on a NeurIPS 2019 paper where this output reachable set computation was first proposed. So we leveraged those techniques, and effectively each if you want to estimate an interval, you need to estimate lower bound, upper bound, and each of them corresponds to solving a mixed integer linear programming problem on the network. Okay. Now, effectively, for this classification thing, you only need 2 points, but that's yeah, that's how we did it.
Okay, thank you.
It's an expensive procedure, of course, because each point, when you compute the intervals exactly, you're solving a mill. And that's why in a follow-up paper that appeared at ECAI last year, done in collaboration with colleagues from the University of Verona in Italy, we moved away from this exact computation and instead considered a probabilistic certification approach. Now, why did we do it? Well, first of all, because we studied in the paper, we studied the complexity of certifying robustness in an exact way. It turns out the problem is NP-complete, hard. So if you want to scale to larger to larger networks, you need to do something different. So we decided to propose an approximation scheme that is based on 2 key ingredients, sampling and statistical prediction of tolerant limits. Now, the idea is that we still start from an interval neural network as an object that allows us to quantify the domain of change. Then we sample from this domain, we observe the result of sampling, and we can derive sort of statistical guarantees on the robustness of a point, right? So for instance, we can say, given an input such and such, the output of the network will be sort of accepted, or will be class C with 95% probability, something like that. Now, with this change, we ran some experiments and we compared the exact approach with this probabilistic approach. Here you see a plot with the 2 colors. The blue columns correspond to the exact approach. The red one correspond to the probabilistic approach. We tested this approach on a number of data sets, tabular data. I only work with tabular data, basically. But this is what we did. And what you see on the y-axis is the magnitude of changes that can be certified by the procedure. In other words, how much can I change the weights in my network before I mess it up, before the counterfactual is no longer valid, okay? So the first result that we observe, that is kind of perhaps not a big surprise, the exact approach is more conservative, which basically means we can only handle smaller magnitudes, right? So we can only handle changes of smaller magnitude. With the probabilistic approach, we can push it up a bit, so we're able to analyze larger sets of changes. But of course, now we're not exact anymore. But the good point is that we increased scalability, and as a result, we could actually test the approach on larger architectures. So here, for instance, in this plot, I'm showing results that we obtained on TabNet. TabNet is a transformer trained to perform classification problems on tabular data. And what you see in the plot is, on the x-axis, number of parameters in the transformer. So we did kind of an ablation study, increasing the number of parameters. We wanted to check how the runtime that you see on the y-axis, how it changes. And you see 2 curves here, the green dashed line, that's a linear increase. The red one is an exponential increase, and the full sort of blue line is the actual runtime that we observed. Long story short, not too bad, right? Because it's kind of following something that resembles a linear increase. And with this approach, we were able to generate counterfactual explanations that are robust for such big architectures. Now, I will wrap up with just a small kind of discussion on model multiplicity, because model multiplicity is related to model changes in an interesting way. Model multiplicity is this situation where you have a data set, and because of some stochasticity, say for instance in the training process, if you train different models, you might end up having models that they're all equally performing, maybe, but they slightly different their internal parameters, okay? And this is exemplified here by the colors in the neural networks. Now, if when you were in this setting, as I said, these models are all equally performing. They're all good. So when you use them to decide whether this person at the top gets the loan or not, they might even agree, all of them, and they all say, no, look, I'm sorry, you don't get the loan. However, computing a counterfactual here introduces some challenges, right? How do you compute a counterfactual here? Do you pick one model and compute a counterfactual for this model? Let's try. This is what we do. This is our counterfactual. And now we run the counterfactual. This counterfactual is computed for the first model, say. We run it through all the models. And what we observe is that the counterfactual is valid for some models in the set, but not all of them. Why is this? You see the one in the middle, not valid. Why is this a problem for recourse? Well, the reason is kind of fairly simple: justifiability, right? The user, of course, the user will not have access to the set of models, but the point here is that you have different models within your set, and these models disagree. So which one do you trust? Okay. Think about generating recourse recommendations. If one model says increase by 50 pounds here in this example, but the other model doesn't agree, then the user might start wondering, which one, who is right here, right? So we have sort of a couple of papers that try to address this problem. The first one is a paper that we published at KR in 2023 with some colleagues from the University of Kent here in England. And the idea for this paper, we used concepts from software verification to analyze, to reason on this problem of robustness to model multiplicity. Robustness to model multiplicity means that you want your counterfactual to be robust for all models in the set or as many models as possible. In this paper, we took kind of a worst case approach. So we want the counterfactual to be valid for all of them. And we achieve this by using product constructions. In a nutshell, a product construction is a composition of your models in the set that kind of, if built properly, allows you to reason about these multiple outputs at the same time, right? And we could use this construction to, first of all, prove some interesting results for us. We wanted to understand how hard it is to compute counterfactual explanations that are robust to model to model multiplicity. Turns out the complexity doesn't change. Long story short, computing the counterfactual for one neural network, feed-forward neural network in this case with piecewise linear activations, the complexity doesn't change whether you have one or several models. It's always NP-complete. And the last point is that you have a product, and this product is a network in itself, so you can dump it into a nice MILP if you're using, for instance, ReLU activations, and you can compute counterfactuals that are valid across the whole set. The very last example, my previous example had a strong assumption that was all models kind of agreed on the initial prediction, right? So in my previous example here, I said, you can see here, all models agree that the loan should be rejected, right? What if this doesn't happen? And that would be the situation here where you see, for instance, the last model would actually accept the loan application. So now how do we generate a good recourse recommendation in this case? This is a problem that we addressed with Jay, the PhD student from that I mentioned earlier, and other colleagues from the department. We decided to propose an approach that is based on computational argumentation. Now, first of all, I'm not an expert in computational argumentation, but also I'm conscious of time. So I will just give you the intuition behind this approach. And then, if you have questions, you can ask. The idea is that you can see this kind of set of disagreeing models as a set of kind of, you can think of it as agents debating, right? One of them thinks the loan should be accepted. The other one thinks the loan should be rejected. And now you kind of want to you want to mediate this debate and find a solution. So how did we do it? We built a so-called argumentation framework out of this set of models and corresponding decisions. And then we use techniques from computational argumentation to reason about this graph and find the largest set of models and counterfactuals that agree. Okay. And this is what we use, this is what we return to the user. Now, all these ideas that I've discussed have been implemented in a library. You see a reference at the bottom. The paper is on arXiv and the library is on GitHub. If you want to play with existing approaches, or at least the ones that we have implemented, or if you have an approach that you would like to be added, let's discuss. But the idea is that robustness has been investigated for a bit more than a couple of years now. There's a lot of interesting stuff happening, but running experiments is always it's a bit of a pain because you have to potentially re-implement approaches or understand what others have done. So the kind of the vision behind this library is to have one common entry point where people can contribute their methods and hopefully speed up research in this area. Right, that's it. So just to sum up, at the beginning of this presentation, we've seen what counterfactuals are, we've seen how they can be used to generate recourse recommendations, and we've seen that most approaches, at least the basic formulations, tend to minimize distance, right? This is done to minimize the effort that users have to put into achieving the desired outcome. However, minimizing distance typically means you lie exactly on the decision boundary, which might introduce robustness problems, right? We've discussed 3 scenarios today in which counterfactuals may lack robustness. There's more, right? So if you're interested in those notions, please take a look at our survey. Or, the book, this, as Yanis mentioned at the beginning, the book is not out yet. It will come out in May, but we have sort of a nice discussion around robustness in explainable AI. Now, this is not just robustness for counterfactual explanations, but also for feature attribution explanations, which is a different class of explanations. QR code here if you want to take a look at other things I've done in the space. This will take you to a list of resources around the topic. And I promise I will shut up now. Happy to take questions.